today. He's a third-year PhD student in our group, and I guess some of you may know him. He's going to present on Tidal Resources Assessment in Larantuka. The floor is yours.
Okay, thank you, Angela. So yeah, my supervisor Gayos B and Palmerah, we are working on the resource assessment actually in Indonesians, but since we focusing in several sites. So one of them is Larantuka. So this is my outline presentation today. So we will talk about the project is going on in this site, and also we're going to talk about my work on doing this resource assessment using DGA search models that has been implemented with the LMADP that has been developed by Professor Holsby, and we will talk about the resource assessment in this area. Okay, this is about the Palmerah Tidal Bridge project. Actually, so in this site, in Larantuka site, so there are projects going on. To be honest, I don't know in what stage the project is going on at the moment. So as you can see, it's easy find it. You find it in the news like this. So this is news from the investment, the news from the engineering site, hydro review like this. They have planned to provide around 115 megawatt in this site from the tidal energy, from the tidal turbine. So where is this site actually? So this is the potential site in Indonesians that we are working on. So one of them is Larantuka, as you see here. So it's some of the papers already review this area. This area has strong current. So this is, I got it from the report. So they have a feasibility report on this side, for example. But unfortunately, there is no complete explanations how the resource in this area. The report is mostly about the bridge itself, the architecture of the bridge, and then everything is not related to the resource assessment. And then they also have this artist impression like this for the turbine itself. And then based on this information, so it's very limited information, we're working on for the resource assessment in this area. And this is the ASIC model that we developed. Okay, so this is the ASIC model. So even though the area is very small here, but we decide to model since very large area because we need to capture this phenomenon as well. This is the Indonesian true flow model. This is part of the global current. If you learn about the oceanography in high school or in the university, or maybe you recognize the ocean conveyor belt, it goes through this area. So since this area has a myriad islands, so it creates very complicated flow pattern. So we need to see this phenomenon as well in our models. Okay. Okay, this is the models. If you zoom into this area, so this is the mesh in this area, and then I calculate the kinetic energy in this area. This area has strong kinetic energy. We can say that. And then as you see the mesh model in this particular site, I try to put it at the same line, aligned with the bridge design. As you see, this mesh here is represent the location of the bridge. And then we run the models and using three different alpha 4, the wave coefficients. So as you can see, this is three different alpha 4 will give us different tidal power output. So we run it for three different alpha 4 and two different blockage ratio. First, is this for the uniform blockage ratio? So this is uniform along the element. So we get the average only 4.6 megawatt. So this is the optimum. So from the 3 alpha 4, we approach it using the SP line curve, and we find that what is the maximum of the optimum average power. And then the maximum is all for the low blockage ratio, not 0.1. We only get 24.8 megawatt. And when we go for higher blockage ratio, we got 19 megawatt and 87's maximum. So it's still not reached 15 megawatt as is planned, as we saw before in the previous slide. Okay, then we move on and we try to do some alternative. We try to see that if we put the bridge here, there, and then these 5 different sites like this, and then this is what we got. So yeah, we also run it the same way as we have bridge locations. We do it in 3 different alpha 4, and we do it in 4 and 2 different blockage ratio. This is what you got. The average here is like this. Even though we combine 5 all different sites like that, we only in total have 16 megawatt. So you can see this even less than when you increase the blockage ratio even in only one site. So the flow is reduced when you put too many arrays in the rows like that. And this is the maximum site of the turbine, the power output. You can see maybe some of area we can reach 100 more than 150 megawatt. But it has to be in higher blockage ratio. It also has to be for more than 3 different arrays along the straits. And then, but there is in consequences like this. So this is for the low blockage ratio. So this is the velocity difference. So this plot is for each. So I calculate the average velocity for the before the turbine implemented in this area, and after the turbine implemented for 0.1 blockage ratio. As you can see, this is the scale. The scale is for the minus, or this is red. So the flow in this area is increased. If it's blue, the flow in this area is decreased. Okay. So this is what happened. If you put high blockage ratio, it's easy for the flow here is diverted to the next channel like this. So you can see the bridge is over here. You put a very high blockage ratio, the flow over here is increased based on just by the existence of the turbine over there. And then when we look for the global ocean conveyor belt here, so this is the parts that we have before from the previous slide. As you can see, this is the site. Maybe I don't know, it cannot be seen here, but you can see this is quite red here. So that means it's increased in some particular area. So it's like when you block this site, it's give effect to this other site, to the other straits. So it's quite sensitive for this, the existence of turbine, quite sensitive to the change of the global current, which is the global current itself will give effect for the global climate too. Okay, this is the other thing that we have to consider about. And then, since the previous one, we used the uniform blockage ratio, which is not realistic. So because in each element, that means you have different turbine size. So in this case, I try to follow their. This is actually another artisan patients, but you can find this turbine specification online. So I try to follow that turbine. So this is the illustrations. So even though actually it's not, it's quite simplifying the shape of the cross section of the arrays like this. So this is but the turbine size will be in the same size. It's uniform. But so that in consequences, the blockage ratio will not uniform in each element. So and then based on this, what we got is the interesting part is you can see this one is bit increased from the previous one with the uniform one, and at the same time you can see this one, not all the channel is occupied by turbines, only partial channel occupied by turbine, because in each side of the strait is very shallow. It's impossible to put turbines. So for example, the turbines that we use here is 10-meter diameter, while in the each side we have 5 meters depth. So we only consider where the turbines can be installed in this area. So that's why you can see the fence length and the realistic fence length is different here. Okay. and then the maximum also. This is the for the 5 meter, and then 5 diameter, and then for 10 diameter. If you see the global blockage here, it's a bit lower. Previously, in 0.1, we got only 4.6, but in here, with only partial arrays and partial strait we occupy that's occupied by turbines, we get 0.0. This is less than 0.1 blockage ratio. But in terms of the energy output here is higher. And then in order to explain that, we have to see the velocity difference between on this case actually. Okay, this is in this side. If you zoom in like this, as you can see, in the area where the turbine is not available, the flow is increased. So maybe previous work has done by Tom Adcock and Scott there for showing that the flow, the model in this DGSR failed to explain what happened to the age of the turbine arrays like that. So maybe this is what happened. Maybe the number is not correct. Maybe it's correct. Maybe because the flow increase that will give effect to some part of the turbine that makes turbine give higher energy. Okay, then the conclusion here. So this is what we got. Unfortunately, it's not. If they say 115 is an average, it's way below that. So the energy available in this area is not that high. But if they say maximum, maybe it can reach that number. But in consequences, you have to put many arrays along the straits with a higher blockage ratio. And since the strait is very sensitive to the flow diversions, if you put some obstacle in the strait, the flow is easy to move around the other sides. It will give effect to the even the small. It will give effect to the Indonesian through flow or global current in this area. Realistic array give higher number of power output, but we still not sure what happened in this partial array along the strait like this. Okay. Thank you very much.
Any questions?
All right, I'm sure you would have said so if you had the information, but is there anything at all about where they got that number of 115 megawatts?
No, I already checked that. They just I think they just get it from the velocity, and then they try to multiply it by number of turbines that can be installed in this area. So, for example, they said, okay, this area can be fit for 100 turbine. They just calculate if one turbine has 1.5 megawatt, so that means they have 150 megawatt, maybe something like that. But I'm not sure. So based on the previous research in this area, there is no interaction between the flow and the turbines. They just do the direct calculation based on the flow itself. Yeah, maybe that's. I'm not sure.
They're going to be badly disappointed.
Yeah.
Chris?
Could you say a little bit more about how you varied the sort of blockage across your fence of the turbines? Because if I understand this is a shallow water model.
Do you mean this for the areas?
Yeah.
Yeah.
So is your model is 2D?
Yeah.
Yeah. So, I mean, doing this is obviously quite important, but getting the representation across the fences is quite difficult because you've lost your vertical dimension to get the variation in symmetry, etc. So, how exactly did you go about going from your sort of idea of varying depth and turbines maybe not staying the full width to how you represent it in a 3D model?
Yeah, it's actually I calculate the cross section here within one element like this. So I compare the cross sections, the area of the cross section in one element to the area that's for the turbines in this area. For example, in this element to element 150 for 10 turbine with the space between turbine is 10 meter and diameter 10 meter, I will have around, let's say, 12 turbines there. And 12 turbines, I'll multiply it by swept area of the turbines. I compare it again to the cross sections of each elements. So I apply that as a blockage ratio in this nodes, and then in this nodes I will compare it with the next node. The average from this node and that node will become blockage in this nodes. So this is how I do it, the realistic arrays in this.
Okay. And were your elements evenly distributed across the width of the channel, or did you have sort of 10 turbines in one element and 5 in another, and then 6?
Yeah, I try to make it even. So, but 150, but it's impossible to make it exactly even. But actually, some of this part is 150, maybe the other part is 145.
Okay.
But it's only very small difference. But it's actually the same.
Yeah. Okay. I'd like to ask another question. You made a comment about some of the rows not producing very much power. Have you looked at essentially what the marginal increase in power is as you add each new array of turbines? Because at some point it will become essentially unprofitable to add a new row of turbines. So you get so little extra power. So have you done any sort of ranking of the marginal improvement?
Yes. Do you mean this?
Yes, I think it's a question of how you interpret what you've got here.
So actually, it's like, as you see here, I think it's related to the flow that we can. The cross section that we can occupied by turbines here.
Okay.
So the number is the big here, but however in here, even though it's because it's a combination with the flow itself and the width of the area of the cross section itself. So it's just based on this I think this is quite makes sense, the result. As you see here and here, even though this one is smaller than here, but the flow here is much higher than in this side. So because it's like funneling like that.
All right. Do you mind if I just sort of respond to Chris's question as well?
Yes.
Because I've looked at these charts and
Yes.
Between us we've looked at them all. If you look at the diagonal row of numbers down the bottom,
Yeah.
that's what happens if you put in each row individually.
Yes.
Average power. It's a low blockage ratio. If you look just below the line where it says A1, A2, A3, A4, A5 at the left hand side, that row is how much you get out from each of those rows if you build all of them.
Yep.
And what you get is that each individual row you get about 2/3 the power.
Yes.
So they're not. But it's okay. They're adding up reasonably well. Now I think you've got the same thing for high blockage ratio, haven't you?
Yes.
So then, this one. So this is effectively doing the same thing for high blockage ratio. So the diagonal rows down the bottom, you go 74, 87, 89, 103, there's big numbers. And then you try to put them all in and you get that row A1, A2, A3, A4, A5, and the 74 has gone down to 18. It's only 25%. So if you have low blockage ratio turbines, you can put them upstream, downstream, because you're not taking out all the resource. But if you have high blockage ratio, it's no good.
Yes.
There's no point having another row of high blockage ratio.
Thank you.
Sorry.
So, thank you, Ahmed.
Thank you very much.